Hello, in the last videos we discussed what is union find and some problems. Let's discuss the next one. Here is the question, read it and give it a try. I will attach the link in the description below. So given an undirected graph with n vertices and m edges, each edge I connects ai and bi. We will erase vertices 1, 2, 3 and so on till n one by one. Erasing vertex I means deleting vertex I and all the edges incident to vertex I from the graph. For each I is equal to 1 to n, how many connected components does a graph have when the vertices up to I are deleted? And the constraints are n is up to 2e5 and m is up to 2e5 and ai less than or equal to bi and so on. So what the question is saying, so let's say this is the original graph. 6, 7 and these all are edges. So this is the original graph and in every step we will remove the subsequent vertex. So in the first step we will remove the vertex 1 and all the edges attach it with 1. So we will remove 1 and we will remove all these 4. So the new graph will be 2, 4, these all. And now in the second operation we will remove 2. So we will remove 2 and all edges incident with respect to 2. So we will remove this, we will remove this and we will 2 also. So this is the new graph that is formed. And now we will, this third operation, so remove the third one and all edges. So this is the new component, new graph, and we will remove fourth one. So this is the new, and we will remove fifth, this is new, and we will remove sixth, this is empty. So at every step we have to return the what are the number of components there. For example, here initially the only one component, and after second operation there are two components, and after three operation, after three there are three, after four there are two, after five one, and after six 0. So I have to print this for all 1 is equal to I is equal to 1 to n. So from this what can you observe that? So we can simply observe that after all the operations the answer finally will be 0, because after all operations we have removed all nodes from 1 to n. So obviously there will be no edges left. So the number of components finally are 0. So it is better to come from last, because we are sure that after all the operations the answer is 0. And what are the number of components just before the last one? It will be simply 1, because there is only one vertex. So gradually as we are removing the vertices, the graph is becoming more small, and hence we can try to get the answer easier for smaller ones than the bigger ones which are initially like this. So from this we got that it is easy to start from the last one, because last one answer is surely 0 and the next one answer is 1, and it is easy to compute answers for smaller graphs than bigger graphs. So after all operation the answer is 0. So looks like last one are easier to find than the first ones. So start from the empty graph and start adding the edges gradually. So let's take an example. So the same example. So this is the workflow. Starting from 1 we are removing every node, we are finding the answer. So let's do the dry run and let's observe something. So initially the graph is empty because we are coming from last. So this is the graph and the number of connected components are 0. And now we are starting to add from vertex from 6 to 1. So now we are at 6. So add 6. So add 6 and connected components are 1. And the vertices still now in the graph are only 6, because we are coming from last and this is the first last one. So obviously only 6 will be there in the graph. And now let's add 5. So add 5. So what are the connected components now? It is 2, because initially it is 6 and now we added 5. So we are adding new vertex. So obviously one component will be increased. So it is 2. And now what are the vertices still now in the graph? They are 6 and 5. And we have added 5, right? But we should add all the edges with 5 that are incident, because how we came from 6 to 5 to 6, we came by removing the vertex 5 and all the edges is incident from 5. So even again when reverting back we have added vertex, it is good, but we also have to add the edges which are incident from 5, so that we will go to the before state. So from the given example, the 5 is attached to 1 and 3, so 5 1 and 5 3. So now should we add 5 1 and 5 3 in the graph? No, because the vertices still now in the graph are only 6 and 5, because all other vertices are deleted. So if they are deleted, it means that the edges are also deleted. So it not means that if we have 5, all edges will be there which are incident with respect to 5, because for an edge to be there in the graph, both nodes should be there, but here only 5 and 6 are there, but 1 and 3 are not present. So it means that we cannot simply add these edges. Now we are adding 5 till now, because we are adding 5 at the present stage. So what are the nodes that are present till now? Obviously all the vertices from n to 6, n to 5 are present, n to 6 are present, because we are adding from the last. So let's say we are adding from 7. So we have added 7, we have added 6, we have added 5. So at 5 what are the nodes possible? Only 7 and 6, because because we are coming from the last. So at a vertex 5, we should add only the edges if there are any edges that are there with ingent other node greater than or equal to 5. That is greater than 6. So 5, so 1 is not greater than 6, so don't add this. And 3 is also not there, so don't add this. So till now only vertices greater than 5 are present. So 1 and 3 are less than 5, so don't add edges. So simply from this we can understand that adjacency of A should contain only vertices greater than A, because when at the position when we are adding A, the nodes in the graph should be greater than A. So adjacency of A should be greater than A, so that we can add all the edges in the adjacency of A. But here 1, 2, 3 are not greater than 5. So simply this will not be in the adjacency as well, because we will construct the adjacency in this way. Input the both nodes and zero based indexing reduce the values, and adjacency of A push back B, because it is given that AI is less than BI. So for example, it is 1, it is surely 3. So only add 1 in the 3. So don't add 3 in the 1, because given 1 is undirected 1. But we have seen that at a stage we are adding I, the nodes that will be in the graph are surely greater than A. So for a meaningful representation of adjacency, it should contain only the nodes which are greater than A. So adjacency of A dot pushback B, because B is greater than A. And now let's continue the dry run. So we completed this and we have added 4. So in the original graph there are no vertices which are greater than 4 with which it is connected to. So no change, but the connected component will be 3, because the before one is 2 and now we are adding a new node and there are no edges, so obviously the answer will increment by 1, so answer is 3. And now add 3, and what is the new number of connected components? It is 4 at the first glance, because before connected component is 3 and now we are adding an isolated node, so it will be 3 plus 1, it is 4. But now in the present graph we have edges 3, 5 and 3, 6 if we see in the given example. So add the edges, right, because we discussed that we got the edges greater than 3, so obviously add those edges as well. So add 3, 5 and 3, 6. So these are the new edges that are added. So initially the answer is 4 without seeing any edges connected to 3, but it is 4. But now we are adding 3, 5, right, because we are adding 3, 5. So reduce one connected component, because initially it is like this. Initially it is 2, but now we are connecting this 2. So obviously the connected component is now is 1, so reduce 1. So now the answer is 3. And also we have 3, 6. So connect 3, 6 and reduce 1 as well, because similarly the before one. So it is 2. So now after adding 3 there are 2 connected components, because 3, 5, 6 is 1 and 4 is 1. So in this way we can get answer for 3. And let's continue for 2 as well. So this is the new graph form. Only now we have 3, 5, 6. So add 2. So when we are adding 2, these edges are already there. So I have marked it in the dark. And it is 2. So now we have edge 2, 3. So obviously we have to add 2, 3 as well. So initially it is 2 before. After completion of 3, the answer is 2. When we are adding 2, it is 3, because we are adding isolated edge. But now when we are going through what are the nodes that are in the adjacency list of 2, we have 3. So obviously connect these to 3 and reduce one connected component, because these 2 are there initially and now we are adding. So the connected will be reduced and it will be 1. Similarly we are reducing 1, so it is 2. After adding 2, the answer is 2 as well. And now let's come to the last one. So this is the graph that is originally there before adding 1. Now we have added 1, and the answer before adding 1 is 2. That is 2. So the new one will be 3. But now the in adjacency list of 1 there will be 2, 4, 5 for the given example. So let's start how we deal with this. So similarly for before 1, we will add 1 for the new edge. We will add 1, 4. So 3 minus 1. Similarly for the before 1 we are reducing, so it is 2. And now we have 1, 4, 1, 2 as well. We will connect this 2 also. And now similarly we are reducing 1 for the before 1 as well. So now the connected component is 1, and we left with 1, 5. So connect these both. So connect these both, and similarly before 1 reduce 1. So 1 minus 1, 0. So the answer is 0. Is this really true? It does not make sense, because after connecting all are connected, so answer should be 1. But why it is 0? What is the mistake that we have done? So for 1 we have 2, 4, 5, right? For 1 the new edges that we have to add are 2, 4, 5. But if we observe this, 2, 5 are already in the same connected component, and similarly 4 is another connected component. So 2 and 5 are same. Indirectly they are same, right? Because they are the same connected component. So let's say this, so for a connected component, we only want one node to make connection, because what is the mistake that we are doing? Here it is 2, it is 1 as well. But now we are adding again. Now we are adding again and we are reducing again 2, again by 1. So final answer is 0. So we want only one node to make connection with all nodes of the component. For example, this is the big connected component we have, and let's assume that data is 2, 3, 5, 6, 1 before example. So if this is a connected component and we are adding 1, so what are the minimum number of edges that are required to connect this connected component with this one? Obviously any one, right? Because if we had 2, 1, it will be connected. If we had 3, 1, it is connected, or 5, 1, or 6, 1. Any single edge is sufficient to merge two connected components. So what is the blunder we are making? So we have reduced -1 for 2 as well, and we are again reducing for -1 as well, because this is the original connected component and we have reduced answer for 1, 2. So is there a need to reduce answer of 5 again? No, because these all connected component, by single edge we can get answer satisfied for this and for this as well. So no need to make this -1. But how to know when to reduce 1 or when to not reduce -1? So now what is the main thing that we want? So we have to represent whole connected component with respect to single node, because only single edge is sufficient. So let's say we have a unique value for component, and let's say that is 2. So it is just enough to connect 1, 2 and reduce answer by 1. No need to reduce answer for -1, 2 for -1, and for 5 -1 again as well. So it is enough to represent whole connected component as a single node and reduce the answer that many times. So how can you do this? So this is DSU, because in DSU we have a ultimate parent nodes for every component. So every time we need the requirement that we have to represent whole connected component with respect to a single node, we can think of DSU. In the previous example as well, the condition is exactly this. So we have DSU. We use the DSU. In the same case as well, we don't want to reduce every edge by -1. We only want to reduce that many times as we have enough number of connected components. So hope you understood this. So let's discuss the last one again. So we have this one 2, 3, 5, 6, and the edges that we have to add are 2, 4, 5, right? So what is the blunder that we are making originally? We are thinking that we have to reduce -1 for every edge possible, but no, because after adding 1, 2, it is indirectly that we have connected 1, 5 as well. So there is no need to do this. So simply by DSU we can find the, for example, this is 1, right? So for 1, 2, 4, 5 are the edges that we are going to add. What is the ultimate parent of 2? So it is 2. What is the ultimate parent of 4? So it is 4. What is the ultimate parent of 5? It is 2. So we can store in a set, because we only want whole connected component to be represented as 1. So for many duplicates, it is simply the single node. So we can use a set and we can store all the ultimate parent components in the set, and we can reduce the answer by the set size, because in this case originally it is 3, and after all the operation it is 1. So we can reduce the answer by s dot size, where s is the set of parents of all the nodes which are in the adjacency of A. Hope you got this. So let's discuss the code. We are inputting n&m and we are initializing parent. We have discussed in the DSU video, and let's initialize the adjacency list. And now we are only adding adjacency of A dot pushback p. We have discussed why we are doing this, and we are pushing the answer, and we are pushing 0 to answer, because finally the answer is 0, because we are removing all the nodes, and count is 0. And for every node starting, increase the connected component, because we have done the dry run, because for every node we have increased 1. So for 0 we have increased 1, for 1, 2, 3, 4, 5. So increase the connected component and make a set. And for the list, so adjacency of list will contain only the one which are greater than A. So we can directly traverse this without any difficulty. So we can traverse this and insert the parent component of this in a set. So after finally we will get the number of connected components we have to reduce. So simply count minus equal to s dot size. And finally we have to merge this as well, right? Because from this how we reached this. So after adding 3, we have added these edges. So how? So we are simply merging those. So merge every connected component of IT with present, so that for the rest of the nodes, the graph will be completely constructed till the before node. So and finally, after completing the J, add answer to count, count to answer. So in this way, we can get the answer and simply print the answer after. So what is fine? Simply it will be it will find the return, it will find the parent of parent that will store in the parent of I. And what will merge do? It will do based on union by size. We discussed in the first video. If the size is large, we will merge according to those and so on. If you have any doubt, comment below. See you in the next video.